we have already finished flow measurements. So today we will be discussing on another topic, that is a pH and conductivity measurement. You know, for liquids and etc., this pH is very important to determine the acidity or alkalinity of any solution or any there unknown test there. And apart from this, this conductivity, which we mean in this case, is actually the electrical conductivity, not the thermal conductivity. That is basically the inverse of resistivity, and we often require to find out how much conductivity is of the solution. That will give you the dissolved ions, the quantity of the dissolved ions, and like this. And they are particularly very useful for pollution monitoring there. Okay. So we'll start with our pH meter. You must have studied basic pH measurement technique, the Nernst equations and etc. But I will be again recapitulating these things and also the engineering aspect or the instrumentation aspect of these things there. So before we start, let us try to understand the theory of ionizing electrode. What is it? When a metal is immersed in a solution of its own ions, a potential difference is created between the metal and its solution. So basically, say suppose I consider a metal which is zinc is immersed in a solution of its own, say suppose zinc sulfate. Then it says that between the metal and its solution, a potential difference would be created. Basically, if we look at it, I say it M0, which is a neutral. When it is immersed in this one, it will be releasing some of its electrons, which is the Z is the valency of metal. And basically, naturally, because of this, the potential difference would be developed between the metal and its solution. Or it could be otherwise. That means it could also be there, a metal ion accepts some electrons and it becomes neutral. Or otherwise, we can say that M plus of Z plus Ze minus, they act together and becomes neutral. Okay. So what we call is that this is either for some metals So either it is like this or it is just the equation is the opposite. And this one, when a metal is they are in a solution, we call this reaction is called a half cell. We'll see that one afterwards. So basically, this we call it a, say suppose, a half cell. So this is also another half cell there. That is the potential difference between the metal and its ion. But it is not possible to measure the potential difference in an half cell. So basically, we cannot do it for a half cell, because once you try to measure it, then the potential distribution will be basically you will be using another metal and the potential distribution would be disturbed. So what we do is that for doing that one, we put two half cells together. And once we put two half cells, it looks like this. Say suppose we have a solution and maybe this is a zinc electrode and this solution is a zinc sulfate solution. Okay. And maybe another one, we use it another metal, maybe copper, and this solution may be copper sulfate. Actually, the zinc and copper, they have the different characteristics. In this case, zinc would be a negative potential and the copper will be the positive potential. That means zinc satisfies this equation and copper satisfies this equation. And we connect them electrically by using, we call it a salt bridge, which is nothing but saturated, one of them is KCl solution. So this comes to be the two half cells and combine together and make it a full cell. And then it is basically these two metals, I can easily measure the voltage across it without disturbing that. And you must be recalling that, be able to recollect what is the bridge name. It is called a galvanic cell. In your school days, you must have seen that one. So basically, a galvanic cell is nothing but zinc sulfate and zinc, one half cell, and copper sulfate and copper in another half cell there. So this one is potential difference is basically E is equal to E2 minus E1. E2 is the zinc half cell, sorry, E1 is the zinc half cell. It is equal to minus 0.763 volt, and E2 is the copper half cell, and the potential is equal to plus of 0.337 volt. You add them together, you get E is equal to E2 minus E1, and that comes to be 1.10 volt. If we recall, that is what the basic galvanic cell, we have it like this. You may ask that, okay, I understand this one and we have studied this one, but what is it relationship with pH meter? Actually, the whole thing, pH meter is also some sort of cell, and we'll see that one, that it depends upon, it tries to measure the ionic concentration of the hydrogen ions, and they can be done using the similar type of cell there. We'll come to it afterwards. But before that, we know possibly you have also come across that the potential developed by a half cell is, what is the value? Though I have given an arbitrary value, this is for a particular saturated solution or like this there, but actually potential developed in a half cell in a half cell, it comes from Nernst equation. It is given as EH is equal to E0 plus of RT by NF into log natural A into C. Okay. Where E0 is the potential developed under saturated condition. But for dilute condition or like this, so what we have further is dT is equal to temperature in Kelvin, N is the valence of ions, then R is the universal gas constant, then F is called Faraday constant, and C is the molar concentration, and A is called activity coefficient. And this is basically A is between 0 and 1. And more dilute the solution is, A is very close to 1. That means if the solution is very dilute, it is very close to 1. And in fact, this RT by NF, this value, giving the values there, it is 2.518 into 10 to the power minus 2 divided by n volts. So this is actually putting all the constant values there. So what we can say is that definitely if it is diluted solution, the half cell voltage is a function of the concentration of the solution. The half cell voltage is a function of the concentration of the solution here. So, in fact, hydrogen, though it is a gas, but it has got the property of a metal also. So, we can think of the hydrogen is also a metal or like this. But the major problem is that getting an hydrogen electrode is difficult. But we can say that the pH means okay, that is the concentration of the hydrogen ion can of a solution should also be able to measure. We will be able to measure by this technique. But what we require is definitely a or any solution what of hydrogen or A there. What we require two half cells together, and basically if we look at it, I can put any other metals or like this, copper or like this. I mean, forget about any A there. But there is a negative electrode, there is a positive electrode, and this we call it a measuring solution, and this we call it a reference solution. That means this is one is a reference cell and one is a, we call it a measuring cell. That means the reference cell, the concentration and all the potentials are constant, all the things are constant, but in a in a reference cell, but the measuring cell, this concentration or this one, there are changing. So naturally, it would be the output voltage E2 minus E1, like this would be a function of this one. But definitely, there is a problem there that it is dependent upon the temperature. So if we can measure the potential, but definitely we can do it, but definitely for connecting it to the relating it with the concentration of the solution, we must take care about the temperature. Temperature must be held constant, or otherwise what we have, that some compensation has to be provided there. So this is basically of the theory of ionization electrode, or like this in a nutshell. Of course, it is much more complicated like this, but for us, I think this will be there. And we will see afterwards that many of the uh, unknown concentrations of solutions or gases can be measured in this manner there. Okay. Now we go for the, as I told, that the pH value can be measured using this one, by this one. And basically, if we recall, the pH is basically expressed as log to the base 10, 1 divided by H, where H is the concentration of H plus ion in a solution. Okay. So in fact, in for pure water, we know that the H is the concentration of hydrogen ion in a solution. It is 10 to the power minus 7 gram per liter. And as a result, what will happen is that it is pH value is equal to 7. And if it is acid, so it would be more. So naturally, pH value will be less because it is 1 by H, and for a base, it will be less. So naturally, pH value would be more. So the pH value is selected in this way, that it is the midpoint is a 7, and this is 14, and this is 0. Here it is base, and between it is acid. So this acidic solution, if the pH value is between 0 to 7 and base is between 7 and 14. We express it in logarithmic scale because we can vary or we can satisfy, get the pH within the range of 0 to 14. Most of the things it will be satisfied there. And so a wide range of variation of concentration can be catered and scaled down to this level there. So this is, of course, but the problem we know that, okay, we understand using this ionizing electrode theory, we can measure some outputs, I mean some voltage which is related to the concentration there. But there is another problem there, that hydrogen gas I cannot use as an electrode. How would you do it there? So naturally that is a difficult one. Similarly, for many other materials also we have some problem there. So we have the problems also there. So the problem is to find out something material which will not be hydrogen gas itself, but some sort of solid material or like this, which when immersed in the hydrogen ion solution or acidic or base like this, they also will produce some half cell voltage which would be very close to the ideal, because these are all theoretically ideal hydrogen half cells. Earlier, the half cells of hydrogen were used with platinum, because platinum was found to be that platinum where if we put it in the hydrogen ion solution, then it will be producing some EMF which is close to the hydrogen ideal half cell. But definitely platinum is costly. So what we go for nowadays, these are called pH glass electrode. So what is a pH gas electrode? Actually, if we look at it, some this it is put of some what we call it some buffer solution, which is providing you some continuity of electrical EA there, and then electrode or lead ware or metal ware, or rather I will say it lead ware, maybe copper or any other thing, or maybe even platinum or gold. But this one is a pH sensitive glass electrode. It is especially made of some glass, particularly we call it sodium glass, which has got a concentration of sodium is more than one. So when we dip this one into a solution of hydrogen ion, between the this solution and between the basically between the two surfaces of the glass electrode, there would be some potential would be developed, and that we call it a half cell, would be that we call it a half cell there. Okay. So this is a basics here there. But definitely what I wanted to say that this sodium glass, something is that here the thin sodium ion selective glass, this is called thin sodium ion selective glass. then the sensitivity is approximately 59.2 millivolt per pH at 25 degrees Celsius. That means if some container vessel is there which is having some hydrogen ion solution like this there, between these two, the outer and inner surface of the sodium electrode, there is a, it will be varying. Inside is a buffer solution which is always constant. It is mostly saturated KCl or something like this. And the only depend outside, it is the hydrogen ion concentration is changing. Uh, so it is a 59.2 millivolt per pH. So it's a good amount, in fact, you can see it compared to the other sensitivity like this there at 25 degree Celsius there. So it is of such, it's a good one, we can say. Uh, it is a good one, but the basic theory is much more complicated. How does it work and etc. So neither I am competent to explain all the things here. So let us, from the our engineer's perspective, we say that this is a pH cell, half cell we call it, and glass electrode where the unknown solution concentration is placed and there is a A there. So this
Sir,
is
sir,
what, yes,
sir, how exactly is the outer and inner voltage difference measured? That I did not understand.
you
You
could not
mentioned.
understand the
You
how
men-
the voltage between this point and this point
yes, sir.
is developed. That's very correct because it cannot be measured. It cannot be measured. For measuring that one, we already told that it is a half cell. A half cell voltage cannot be measured. We require another half cell to measure the voltage. So what we do is that this is called a measuring cell. We have another, we call it a reference cell. So it is a measuring half cell. Think of that same way we had discussed about the there, galvanic cell. It is basically, okay, I put it in this way, that is a reference half cell. I think I just put it in this way, what it would be reference 1 and etc. I will come to this one another there. And these two must be electrically connected. And this is a, what we call it, a salt bridge. It is called salt bridge here. So naturally now we can say that these two, because this is connected to the outer one potential is connected electrically to this point. So the same potential of the other one. And the reference half cell, that means here it is a constant concentration, anything there, and this is it, we know what is the potential that is known. So between the terminal A and terminal B, I can get measure the output voltage. I can connect a voltmeter and measure this voltage there. So as I told that we always need a two electrodes. One single electrodes cannot be used. There are two electrodes. One is called reference electrode and one is called the measuring electrode. But the basic difference between them is that reference electrode will always give you a constant potential, develop always a constant potential. It is always better that it should not change with temperature. It should not change with any other things here. Huh. But it will be always a constant potential here. But in the measuring one, the potential across the glass electrode surface will change from the depending upon the hydrogen ion concentration. So we have these two terminals across which we can nicely connect a voltmeter and measure it. Is it okay? Yes?
Yes, sir. Yes.
Huh? It's okay. So now definitely it is a area. Always it is required two electrodes, otherwise we will not be. Actually, sometimes they are called, I mean, two electrodes are there, sometimes they are combined together. They call it a combination electrode, in house together. So that is a further advancement or like this there, but these are the area. So what we require for the reference electrode? We require that it must satisfy certain criteria. That requirements, one must be potential should be independent of H plus ions concentration. Number one, should not vary with temperature, and third one, should not change with time. That means it should always be constant. It should not, with time or with aging, it should not vary. Only what we want is that reference measuring electrode, it should vary the concentration. And apart from that, there are several maintenance required for the measuring electrode, because sometimes over the glass there is some coating is there. We require some acid cleaning, or it has to be dipped into for some time some low concentration hydrochloric acid to clean it. So those things are there, but reference electrode must be held constant of this one. And naturally, there are only few which qualifies for this one there, which we call it the reference electrode types, which we can have. One is calomel, which is mercurous chloride. Can you see it? Mercurous chloride. It is an amalgamation. And another one is silver chloride. Okay, and a reference cell looks like a calomel's reference cell, looks like this, though I have shown it in this manner, but actual reference cell. So it is not the actual reference cell, it looks like this one. You can see many books there, those details are there. So this is what it looks like. This is definitely the lead wire. And this calomel is obtained in terms of granules or like this there. So through which I just put it, put the wire here. At the bottom there is some glass well, and the inner tube has a uh, hole which gives you some electrical connectivity or conductivity there, and the outer solution is saturated KCl solution. So basically, where we wanted to measure is that same solution. Basically, if we look at it, it would be in the same solution. I connect them, the reference cell. This is your A, this is your reference cell. So, there is a hole and I call it a salt bridge. So these two are connecting, so giving a potential of this one, electrical connectivity. So at least from B and A across these two terminals, we get this one. And this is one Nernst equation, and there is another potential, which is also another Nernst equation. But ultimately what we say is that everything is constant. So, only with the hydrogen ion concentration difference, we would be able to measure this voltage there. Okay. So, similarly, the calomel and silver chloride has also similar construction in it there. Okay. But there is another catch there, which we need. So, this is this part. So, this should be this reference and measuring cell both should be, can be separate, they can be housed together in a combination electrode, but this has to be, both of them should be in touch with this one concentration, and we get a voltage there. But I would rather concentrate on what should be the uh, instrumentation point of view. Okay, we will try to how, what are the problems which which may come across up to this one there. So what we can say is the instrumentation measuring problems with measurement or measuring circuit. We can have always, there should be a temperature compensation scheme should be provided. We have seen it that in Nernst equation it is dependent upon the temperature. So if the temperature changes, the potential changes. So naturally there would be a problem. That has to be, if you cannot keep it constant, you better sense the temperature of the solution using a thermistor or any other temperature sensor and compensate it using some compensating circuit. But more problem is another case there. You can think of, okay, this is a voltage 59.52 millivolt per pH. So if there is a pH variation and like this, I can connect a voltmeter. Simple, our laboratory type voltmeter or digital voltmeter or like this, using that one. But I tell you, if you connect a normal laboratory type voltmeter in this case, then there would be almost, you will get almost no reading or zero reading. This is one case example where I can say that even if the instrument is good, because of your improper measuring scheme, it can fail to give result. So I say that this is even if this looks to be nice and like this, if I connect a voltmeter there, standard voltmeter there, laboratory type, you will get a almost zero voltage. Why? Can you guess? Any idea? This is because anything we can say we have studied in measurement or even first years also. So this pH electrode, which will give it the EPH, some potential, say this is plus and minus there. And it will have an internal resistance Ri, and I connect a meter Rm there. And I measure what is the voltage there. We know that for avoidance of the loading effect, you must have the Rm, a thumb rule, is approximately 10 times Ri, at least. At least should be much higher because otherwise the voltage will drop there. But, so a digital voltmeter, what is the, for a digital or electronic voltmeter, what is the A resistance Rm? I can take it 1 to 10 mega ohm, anything between, because it depends upon the quality of the meter you want to use. It could be 1 mega ohm if it is a low quality, or it could be 10 mega ohm. Now the question is that what is the value of Ri? If we look into this one, say suppose between this point to this point, there would be a very small amount of current flowing through that one. But if it has to pass a current through this path like this and go through it, the current has to pass through the glass electrode. This is your glass electrode. So it has to pass through glass electrode. And as a result, the internal resistance of Ri is very high. Of course, you can have the salt bridge and all the things are electrical connectivity, but these two, the glass electrode from this point to this point, is very high. And as a result, what will happen, this Ri reading is that approximately, you can say, in the range of 10 to the power 9 ohm. That means some in the range of giga ohm there. So if it is 1000 times more this one, so naturally what we will get, the output, there will be a total loading effect and output voltage will be zero there. So we cannot use the normal voltmeter or like this. Rather we require a special, obviously we require a special measuring circuit with very high input impedance. That means it should be in the range of at least 10 giga ohm or more, that one. That is a big problem there. We normally use FET input amplifiers because FETs have got much higher, but it also requires a special FET configurations and etc., which can give you at least 10 times more than that one there. And not only that, we require also special moisture resistant lead wires. because this lead wires will take you there, but these lead wires will have the insulation. This is this insulations often the insulation resistance is also often in the range of 1 mega ohm or 5 mega ohm or like this there, 10 mega ohm. So that will not do insulation resistance to be much higher. And in fact, if there is moisture, this insulation resistance will go down. So we should not allow that one. So naturally, the principle looks to be very simple, but the measuring scheme is much more complicated that we can see it like this there. So that is a very important thing. We must look for the pH circuit and here there for a pH measuring circuit. And these two things must be properly other here there. Otherwise, even though electrode is good because of their lack in measurement schemes or the incompetence of your measurement scheme, we can have the big problem there. I think I will stop here. Of course, I could go through some more things, but I will not be able to complete that part. Uh, So there would be similar techniques are there for oxygen ion concentration. I will tell you in the next class there. So any question till now? Is it okay?
Sir, in
Yeah.
earlier circuits, we used to use a op amp to amplify it and then measure, right? So in this also, could we use something like that?
We can use op amp, but you know op amp internal resistance is also in the order of few mega ohm. Of course, some are there. If you look at it, LF411, that one is a FATE input op amp. There we can have, I don't recall, it is around 30 mega ohm, but we require far more. So basic special input, and there at the input stage, they use instead of BJT or like this, they use some FATE here. It's very special configuration. So input circuit stage is very large, very complicated and much more here there.
Yes, sir.
Complicated.